Okay, welcome to the next section of the myocardial mechanism lecture. We're going to talk about the second half of the cardiac output equation, which is now heart rate. So we've talked about stroke volume and all of the mechanisms which causes isoblumic contractions, ejection, filling, all of that in the heart. Now we're going to be talking about heart rate. Okay, so the most important factor that influence the number of cycles per minute is our autonomic nervous system. Point of origin is within the medulla, which we have something called the cardiac accelerator center. In this center, this is where our sympathetic nerves originate. Sympathetic nerves are going to terminate on 4 locations in our myocardium. 1, the SA node. 2, the AV node. 3, walls of our atria. And 4, walls of the ventricles. In these locations, we are going to have receptors that are going to be sensitive to the sympathetic neurotransmitters. They're called adrenergic receptors. Our sympathetic neurotransmitters will act on those adrenergic receptors. What are those sympathetic neurotransmitters? Norepinephrine and epinephrine. They are going to act on the beta-1 receptors of the heart. That's important. So norepinephrine and epinephrine as neurotransmitters coming from our medulla of the brain and our cardiac accelerator center act on beta-1 receptors of the heart. So when we talk about norepinephrine and epinephrine, they're classified as 2 different things. Norepinephrine and epinephrine can be neurotransmitters from the sympathetic nervous system, or they can be hormones, which are sympathetic hormones within our hormonal system and our endocrine system. So I don't want you to be too confused. Norepinephrine and epinephrine can be considered neurotransmitters and also hormones from our endocrine system. When we talk about norepinephrine and epinephrine as neurotransmitters, the dominant neurotransmitter at 80% is norepinephrine compared to the 20% is epinephrine. Now, when we talk about the endocrine system and them as circulating catecholamines, that's what they're classified as catecholamines when they are hormones, that will switch. The dominant catecholamine as sympathetic hormones, epinephrine is 80% dominant, and then norepinephrine is 20% dominant. So that is where they flip-flop. All right, so let's continue on with our autonomic nervous system. It has 2 parts, sympathetic and parasympathetic nervous system, right? So it's branched into 2 different sections. We need a balance between these 2. If we want to turn on one, we have to shut off the other because we can't accelerate and decelerate at the same time, right? So our sympathetic nervous system influences the rate and force of contraction, and it influences how much calcium is going to enter the cell. The nerves that come off the medulla will branch off the spinal cord into the cervical and thoracic region. The medulla also has what's called a cardiac inhibitory center. This is right next to the cardiac accelerator center. So what comes off of this is cranial nerve 10, which is our vagus nerve, which is considered our parasympathetic nerve. All right, so let's talk about our vagus nerve and the parasympathetic nervous system for a second. This vagus nerve actually terminates on 3 locations of the myocardium, right? 1, our SA node, 2, our AV node, and 3, the walls of the atrium. This binds with cholinergic receptors because the parasympathetic neurotransmitter is acetylcholine. This slows everything down for us. So when I just talked about our sympathetic nervous system, those nerves terminate on 4 locations. The vagus nerve, which is our parasympathetic nervous system, terminates on 3 locations, right? So vagus nerve terminates on the SA node, our AV node, and the atrium. Again, this is going to bind with cholinergic receptors because the parasympathetic neurotransmitter is acetylcholine, and this is what's actually going to slow down for everything for us. So this is going to slow down heart rate. Okay, so let's talk a little bit more about the regulation of this cardiac cycle. The quantity of blood being ejected by the heart into the systemic circuit can be altered by two things. Again, pretty much what we're talking about is cardiac output. So the two things that it can be altered by is the change in heart rate and a change in stroke volume. Again, the stroke volume is the amount of blood ejected during each systole. A change in one of these parameters usually has a change in the other. So the relationship between the two alter cardiac output, again, which is heart rate and stroke volume. So if we drop heart rate down to less than 50 cycles per minute, we will actually not compromise cardiac output. Why is that? Is because stroke volume will then increase. Okay, so our heart actually has an intrinsic rate, right? So our intrinsic rate of the heart, or our myocardium, is 100 cycles per minute. So this means if we actually were to take away all nervous and endocrine factors, our heart would actually naturally beat at 100 cycles per minute. So if we removed parasympathetic and sympathetic hormonal and neurotransmitter influence, our heart would naturally beat at 100 cycles per minute. But not many people have a resting heart rate of 100 cycles per minute. And why is that? It's due to our parasympathetic nervous system, our vagus nerve. Here, acetylcholine is actually slowing it down versus our parasympathetic nervous system. It is attaching to those cholinergic receptors within the heart, and it's actually slowing down cycle rate. And again, remember, the parasympathetic nervous system, the vagus nerve, terminates on our SA node, AV node, and the atria. And it's really important with regards to cycle rate because our SA node is what's giving out each cycle, right? It's giving out each cycle per minute. It's giving our beats, our cycle rate, and all of that. So when the vagus nerve also terminates on that, acetylcholine can slow down cycle rate. So let's briefly talk about how the brain influences heart rate. There's other sections that can influence cycle rate as well. So our frontal lobe, which houses our limbic center and our emotions, so emotions and our limbic center can affect cycle rate. Our orbital portion of our cerebral cortex is what we see. That can impact it. Our motor cortex controls physical activity, so that's going to influence cycle rate. Our premotor cortex if you remember, sets the stage for our motor cortex, right? Our hypothalamus is where our thermoregulatory center is. This is where we detect hot, we sweat, cold, shiver, all of that good stuff. And we also have a cluster of cell bodies within the diencephalon called the fields of Ferrel. This influences heart rate. This is what causes us to shiver. All right, so let's talk about our medulla for a second. The dorsal region of the medulla has two centers. Our cardiac accelerator center, this is actually going to influence our rate of cycles, and then our cardiac augmented center. This regulates actually our force of contraction. Okay, so next we're going to talk about something that's called Mary's Law of the Heart. Okay. So this is considered a baroreceptor reflex. Okay, so the cardiac accelerator center can be influenced by this. So again, cardiac accelerator center we're talking about cycle rate, so cycles. There is an inverse relationship that exists between arterial blood pressure and heart rate. We know systolic blood pressure increases during exercise. Why? Because we are putting more fluid into the tubes. So therefore, increase in fluid, we're putting an increase in pressure on those receptors that are within the vessels themselves. So we're going to have an increase in pressure. So baroreceptors, where are they located? They're located in our aortic arch and in the carotid arteries, and they influence cycle rate. Right? So the more stretch we put on these receptors, the more influence they will have on cycle rate. So if we sense an increase in blood pressure, those baroreceptors will send a signal to the cardiac accelerator center in the medulla and will cause the cardiac cycle rate to slow down because it will ensure the fact that for a moment in time, there will be less volume in the tubes. That decrease in volume in the vessels will help us bring pressure back down. The exact opposite actually happens if we become hypotensive. So if the amount of stretch placed on those baroreceptors dramatically decreases, then they will send a signal up to the cardiac accelerator center and will cause an increase in cycle rate. So this is where that's that inverse relationship. So actually that is a protective mechanism for us. So when we become hypotensive, it ultimately means we're not putting enough stretch or pressure on those baroreceptors. So that means we're not ejecting enough volume to put the proper amount of stretch onto those receptors. So our body and those baroreceptors will actually detect that they're not being stretched enough when we become hypotensive. So that's why those baroreceptors actually send a signal up to our cardiac accelerator center saying we need to increase cycle rate because we need to put more pressure onto those receptors and help get more volume into the system of blood. So that's where it's kind of a protective mechanism with us. And that's where it goes the opposite way. Okay, next we're going to talk about a Bainbridge reflex. This is considered a volume reflex. We have some volume receptors that are sensitive to stretch within the myocardial walls. These are located within the atria, actually right where the vena cavas come in to the right atrium, and where the pulmonary vascular comes into the left atrium over here. So those are where those volume receptors are located over here. Right at those locations, we have pressure sensors, which are going to respond to a change in volume. They're called pressure sensors because the more volume you put in, just like we talked about, there will be more pressure on the walls. The pressure on the walls within the atrium will stretch those receptors. This will cause an acceleration in heart rate. Okay, because whenever there is an increase in pressure sufficient enough to distend the right side of the heart, this is attempting to take the stretch off of those receptors, and by doing so, will allow heart rate to come back down again. So during exercise, we will have enhanced venous return, right? So we're going to have enhanced blood flow returning to the heart, right? That's what venous return means. Causing distension of that right side of the heart due to more volume of blood. So now we're talking about exercise. We're enhancing venous return, more volume coming back. We're going to distend the right side of the heart due to more volume coming in, so we are going to put more of a stretch on those receptors. This will cause an increase in cycle rate in attempts to bring the pressure off of those receptors because we have so much volume coming in. And in doing so, cycle rate can then come back down. The magnitude of the heart rate response will be determined by what the heart rate is when the pressure-sensitive volume receptors are actually activated. So if we have a heart rate that is already slow, an increase in fluid will accelerate the heart rate. If heart rate is already high, then an increase in fluid will actually slow heart rate back down. Okay, we're going to finish up talking about these volume receptors. Okay, and then we're going to move on to some breathing mechanisms in the next screencast. So if these volume receptors that we just talked about are activated enough, they will actually trigger an increase in urine production. They will increase urine production as a result of their impact on the antidiuretic hormone, so ADH. ADH is actually then reduced by the posterior pituitary gland, right here. And the more ADH that you have circulating within your system, the less urine you produce. So the less ADH you have, the more urine you produce. So when we exercise, there is an increase in the ADH when we thermoregulate. When we exercise in the heat, we increase the amount of ADH being released. Right? This makes sense when we're exercising or when we're in a hot environment or a hot, humid environment. We want to conserve fluid within our bodies. So we have that for thermoregulation. That's really important. If we activate these pressure-sensitive volume receptors enough within the heart, we then will see a decrease in the release of ADH. This causes an increase in urine production. Why is that important? This is our body's way of eliminating fluid from the body in attempts to take pressure off those receptors. So sometimes when we enhance venous return to a great extent, we're going to increase urine production because our body is thinking at this point in time, we have too much volume, we have too much fluid within our system, so we need to get rid of it somehow. We need to excrete it out. So then that's when will happen there. We will decrease the release of ADH, and by decreasing the amount of antidiuretic hormone, then we increase urine production. So that makes sense if we're in a hot environment and we don't urinate as much. One, it could be the reason if we're dehydrated, but two, it's we are actually increasing the release